In this amazing video, we examine subqueries. A subquery is a simple standalone query that can be embedded inside another query to provide information to the containing query. With a subquery, we can provide results to another query, or we can filter the results of another query. Most of the things we can do with subqueries can also be done with outer joins or filters, but this is an interesting technology that you will see other people use. Therefore, it's important for you to be able to read and write subqueries. You may not use them on your own. You may decide that they are not effective. You may decide they are not necessarily readable, or you may fall in love with them and you may use them all the time. Either way, you will see them in other people's work, and given that a lot of what we do is maintenance on existing work, it's important that we understand how to use and how to create subqueries. Looking at the AP database, taking an example from your book, we see that we can use a subquery, here highlighted in yellow, as a filter. In the where clause of the main query, we are selecting the average invoice total value from the invoices table. In other words, we are averaging up all the values in the invoice total column across all the rows in the invoices table. That is one value, and that value is used as a minimum qualifier for the where clause in the select query. What we're saying then is I want only the invoices that are greater than whatever that computed average value is. Here, the subquery is highlighted in yellow. We are actually writing two queries, and I think it's important and helpful and useful to debug them and develop them as two separate queries. Particularly, develop the subquery first, make sure that it works, and then embed that into a working superquery, if you will. The superquery can be written almost completely without the subquery. In this case, just remove the where clause completely. Get that to work, build up some confidence that that's correct, and then add in that subquery that we have already debugged. Here's an example. We knew that we needed the average invoice value across all the invoices in the invoices table. Therefore, we wrote that select query to generate that average. It's an aggregate query, something that we've already learned in a previous exercise. That aggregate query seems to work. We may look at it and do a sanity check on it. $1,879.74 appears to be right. We may take a glance at the data. The data may be overwhelming. There may be thousands or millions of records, and it's physically impossible to guess whether that's correct. But the formula is correct. The syntax is correct. It returns a numerically correct value. We have some confidence that we probably wrote the query correctly. And then we, without writing the entire query, we write the superquery with the where clause commented out. As you can see in this slide, we took everything out of that superquery, commented out the where clause, and ran that. And that appears to give all the rows from the invoices table and the three columns in which we are interested. That appears to be correct. That looks reasonable. Once that is perfected, we paste back in the where clause with the subquery, and we have some level of confidence that one working subquery and one working superquery probably creates a reasonable result. Let's take it a step further just to build on our discussion of subqueries. We know that, let's back up to the previous slide again, that we are interested in invoice number, invoice date, and invoice total, which are all values taken directly from the invoices table. And that's terrific, that's useful, that's very interesting information, but as a database developer, you're probably learning to anticipate what the next question would be once you've answered that question. And we can probably assume that at some point we will be asked to provide the vendor tied to this information. In the invoice table, there is very little vendor information. Let's flip over to SSMS. And I'm logged in to our server. You are encouraged to log into our server as well. Use the AP credentials and you can follow along with this work. In the invoices table, we see that there is a vendor ID, which is a foreign key into the vendor table, but not much more. In order to answer the question, who are the vendors, we need to drag in the vendors table into this query. Showing the vendor ID would have no value if our customer wants to know who are the vendors. So just simply adding the vendor ID to this query doesn't do us a lot of good. In the next slide, you can see that we expanded on our previous example by doing an inner join with the vendors table on the common field. Primary key in the vendor table is vendor ID, foreign key in the invoices table is vendor ID. We've still got the subquery, and that still works terrifically, but we're joining two tables in the superquery, the vendor table and the invoices table. And because we're joining those two tables, we can extract the vendor name and include that in our results set. So let's grab all of this code and let's paste that in to see that it works. Now we have three beautiful columns in our output. Two of the columns come from the invoice table, invoice date and invoice total. The first column comes from the vendor table, which is vendor name, and that answers both questions. The vendors that are attached to the invoices and the invoices themselves. Therefore, we have expanded on the original example in the slideshow by doing an inner join along with the subquery that's tucked into that where clause. This works well. It's easy to read because it's a simple query, and the subquery is easy to spot because there's a select statement in the where clause, and it's indented. We've written it pretty well, but it could still be better. Remember that our job as developers of any kind of software is to create software that is maintainable, reusable, and readable. Because we want to use things more than once, we want to work as efficiently as possible. Well, we can make this a little more maintainable and readable and reusable by breaking that subquery into its own separate standalone query. Now, to store a query in SQL Server, we do something called creating a view. The view is simply a stored, named select statement that lives inside the database. I know a lot of you at this point have probably typed something like this and then did a file and a save, and you got this, but that's not the best way to work necessarily, because you're saving a standalone file on the hard drive. You're not even sure what file system this is, and it doesn't follow along, it doesn't persist inside of the database container. It's not part of the AP database. It's part of your work, which is easily separated from the database. While it's a good temporary solution to save your work, and as you can see, it's on my computer, not on the SQL Server computer in the cloud. This doesn't necessarily provide the most efficient and professional way to do things. So what we want to do is we want to take this subquery and eventually the entire query and save those as part of the database. The subquery we'll do first is easy enough to do by creating a view, pasting in that subquery code that we already wrote, and saving that in the database. So let's grab just the select statement. And now we'll do something new. We haven't done this, or if we have, we didn't talk too much about it. Let's go to Views, New View. I right-clicked on the View folder. I selected New View. At this point, you probably realize you can't do this because you don't have permission, so you'll just have to watch. Close, paste. I pasted that subquery directly into the definition of the view. And if I click off of the SQL window here, up into the top pane or even the middle pane, it builds a little graphic representation of my view. And I can actually execute this. Right-click, execute. And there's the same result that I got earlier when I debugged the query by hand. But now it's called a view, and I can save it if I click on the close button of this tab. This is a different kind of save than we've done before. V, and what did I call it on the slide? V average invoice total. It was already there, I'll just overwrite it. And if I look under Views, there it is. So I took my subquery that I wrote by hand, that simple select statement, I made it into a view, and watch, I can run this view. Right-click, select top 1,000 rows, there'll only be one row. And there's the result of that view. This is a little bit beyond the scope of the class, but the point here is that we can write subqueries as views to make them more reusable. That's what I want you to take away from this. And look at the slide, you can see that there was something called invoices above average, which is the answer to this question. It's the exercise that we already derived a few minutes ago. So let's look at the design of that. You can see that the SQL that defines this view is almost exactly what we wrote on the slides that we wrote by hand. It's a little different because SSMS and SQL Server add a little bit to it, but it means exactly the same thing. And I can run this, and it doesn't work. Well, through the magic of time management and editing, I fixed it. But the point is here, the point is that a subquery can be defined as a named view and used as a subquery in another superquery. Will you be doing this for me in class? No. But the theory is important and the practice is important, and I want you to grasp one of the reasons why it's a good thing to create subqueries. So we don't worry about optimization. We don't worry about scaling at this point. We're just worrying about the mechanics of it, and the mechanics of it are that we can create a named query called a view. We can use that as a subquery to write readable, maintainable, reusable code. Here's another subquery example. On page 189 in the book, the question is asked, what vendors do not have invoices? In this case, we're using the AP database again, and we are using a not in expression. We're saying that give us all the vendors from the vendor table, but filter that by only vendor IDs that are not in the invoices table. You should recognize this as something we can do with a left outer join or right outer join, depending how you list your tables in the select or the from. But if we don't want to do it with an outer join, we can do it from a not in. Which is better? We'd have to study the query optimization that SQL Server goes through to see if one might run faster than another. If we had millions of records in our database, that would be a serious consideration. Is a right outer join going to be faster, more efficient than a not in against a subquery? That's not part of the scope of this class. We won't discuss that at this point. The syntax here is at issue. The syntax is using a not in to reference a subquery to filter the results in the superquery. In the next slide, we ask the question, what invoices are larger than the largest invoice for vendor with ID 34? We're assuming that ID 34 has some meaning to us. I don't know what vendor that is off the top of my head. I do, but I'm acting like I don't. We're using the AP database. We're selecting 3 columns. Note again that 2 of the columns are from the invoice table. 1 of the columns is from the vendor table. We're joining invoices and vendors together on the common field, which is vendor ID. And we're filtering. We're using our where clause. In this particular where clause, we're selecting rows from the invoices table filtered on vendor ID equals 34. And whatever rows come out of that filter become the results set returned by the superquery. The all keyword means that every row selected in the superquery has to match that condition established in the where clause. So every row in that inner join has to have an invoice total that is greater than every row in the subquery. Again, every row in the inner join has to have an invoice total that is greater than every row in the inner join or in the subquery, which is all the rows from the invoice table with vendor ID equals 34. That answers the English language question, what invoices are larger than the largest invoice for vendor with ID 34, which might be useful information if you want to know who's spending more money, who is billing more than whatever vendor ID 34 is. In the next example, we look at using the in keyword. Make sure you can differentiate between the in keyword and the all keyword. In this case, we're looking for a single match, not a complete match. The English language query then is what terms are not used in any invoices. Terms are how long the vendor gives you to pay the invoice. A vendor may give you 10 days from the day that you receive the bill. They may give you 90 days from the day that you receive the bill. Terms are negotiated by the vendor and the customer. Or if the vendor is a big, humongous company, they may set the terms and you may not have any choice. Trust me, don't ask me how I know. To break this down then, We need terms that are not being used. In other words, we need terms that do not show up in the invoices table. What we can do then is select all the terms in the terms table and then look for a subquery that doesn't match against the invoices table. And here is one way to do that. We're using the not in keyword. We're saying give me all the terms rows, but let's look at it again. Only give me those terms rows that don't show up in the invoice table. If a term is used in the invoice table, we don't want to see it. We only want to see the ones that are not used. So the subquery is a distinct query. Give me all the terms from the invoices table, but only give me one copy of each. We're not going to get 20,000 rows from the invoices table. That result set will be very small because there are only a few rows in the terms table. So let's grab that, copy it, flip back over to SSMS. Let's clean this up a bit. Here's our query. We pasted from the slide. Select terms ID, terms description, and terms due days from the terms table, but only where the terms are not used, where they do not show up in the invoices table. And this is a little different from the slide. I went ahead and added another term so that there would be a valid result. The slide demonstrates the same information, but you can see that there are no results because there were no terms that were not used in the invoices table. I went ahead and added infinity, meaning you never have to pay your invoice, which might be nice if you were the customer, but not if you're the vendor, just to see that we get some results. When you run the query then, it grabs every row from the terms table. Then it grabs every row from the invoices table, but it does not bring in duplicates of the terms ID. Then it intersects those two tables. You can see hopefully that this could be done with a left outer join of the terms table and the invoices table. And I would leave that as an exercise to you at this point. You should be able to write a left outer join between those two tables to solve this problem. Our next topic is correlated subqueries. Correlated means that the subquery runs once for every row in the superquery, referred to here as a main query. You can see this could get pretty hairy because you're asking SQL Server to do a lot. You're asking it to rerun a subquery for every row in the main query. And if the subquery is an aggregate across an entire table or set of tables, this could become a real drain on the resources of the database engine. Should you never use these? I would never say not to, but I would say be aware of what you're doing and be aware of the burden you could be putting on the database engine. We're interested now in syntax and getting simple queries to work, understanding how to write correlated subqueries. We're not as concerned about scalability. If we're running this query against 100 million eBay auctions, this query may take 3 days to run. It may cause a lot of consternation because no one else can do anything while the query is running. But that is not our concern at this point. Here's an example again. For each vendor, what invoices are higher than the average for that vendor? We need to consider each vendor individually. That would be the super query, the outer query. And then for each given vendor, we need to calculate the average for that vendor. That is a clear indication that a correlated subquery is necessary. The subquery here, highlighted in yellow, contains a reference to the main query, to the superquery, right here. And I named the aliases of the tables as main and sub, rather than just I's and S's and very short abbreviations, to allow you to see very clearly that in the subquery is a reference to the superquery. And because of that, the database engine knows it's a correlated subquery. If you look at the select statement at the top, we're selecting from the invoice table and aliasing that table as INV main. And then in the where clause, we are running another select query for every instance of rows delivered in the main query. And the where clause in the subquery contains a reference to the subquery table, INV sub, and the main query table, or the superquery table, INV main. That tells SSMS and SQL Server that it's a correlated subquery. Let's grab that code. And let's paste that in. And that doesn't work. It appears I have made some kind of copy-paste error. Let me flip back to the slide and grab this again. That looks better. Somehow that order by got jumbled up. And there are all the vendors and their invoices, where the invoice total is greater than the average for that vendor. Is this correct? It's hard to say. We would probably have to do some study and some little tiny individual research queries to figure this out. We'd have to perhaps focus on a vendor, compute the average for that vendor, list all the invoices for that particular vendor greater than that average. But it appears to be reasonably, possibly correct. If I give you something like this, I would certainly examine the SQL that you wrote and hopefully give you something to go by, and I would give you a fighting chance at getting it correct. In the real world, there's a little more to this than just writing the query and looking at the results. Certainly, we'd have to do some study. But I will tell you that sometimes it's just impossible to manually verify every row in a million-row table that we got everything correct. But this looks to be reasonably correct. Here's another nifty correlated query. In this correlated query, we're using not exists, and we are referencing the vendor ID from the main query. So we know it's a correlated query because there is a reference to a table that is not in the subquery, so it must come from the outer or main or core or superquery. The question being answered is, what vendors do not have invoices? The first thing we do is grab all the rows from the vendors table. Easy enough to do. Pick 3 columns. Notice we're picking the vendor ID column even though we're not particularly interested in the results set, because we have to use it down here in the subquery. After we've got all the rows from the vendors table, we throw in a where clause, and we're saying I only want vendors that don't show up in the invoices table. Hopefully you realize that this can be done with a left outer join and a null or a not null in the vendor ID field. I would leave that as an exercise to you. Make sure that you can rewrite this as a query with a left outer join rather than a subquery. We grab this code Paste that into SSMS. We get all the vendors that are on file in the vendors table but have not billed us. They haven't sent us any invoices. That's a reasonable real-world scenario. We add vendors to the vendor table as the vendors become approved by purchasing. They may have to go through a process of approval where they submit proof that they're in business and they submit proof that they can supply what we need them to supply. Then they get added to the vendors table, but they may not have sent us an invoice yet. Therefore, this is useful information in the real world if you're in the accounting department. Here's another question that is interesting. What states do not have vendors? Now let me skip ahead before we address this. At the end of the slideshow, I provided a script, and this is SQL, but it's not a select statement, it's an insert statement, I believe, that you can use to create the states table. If you look at the AP database, you can see a table there called state, and it's a little bit special because it's not part of the standard AP database that you can download. It just has the states in it. It has the states and state abbreviations in it. I provided that just to give us more flexibility and provide more information so we can write more interesting queries. I encourage you to grab this entire query. So Control A, copy, and then go back here and run this against your database, okay? Whatever your database is. Because you can't create tables in my database, in AP. However, you can create tables in your database because you own it. Run that query and you can see how it creates that table and populates it with state abbreviations for all 50 states plus Puerto Rico and Washington, D.C. as well. It would be an interesting exercise for you. All right, back to our topic at hand. The question we'd like to answer is, what states do not have vendors? I would like you to be able to do this using a correlated subquery and using a left outer join or a right outer join. In the next slide, I will give you the subquery using the exists keyword, and then I will give you in the following slide the query that does not use subqueries but does use the left outer join. You may stop the tape now, stop the recording now, and try to write those queries, or you can skip ahead and look at those queries because I don't know which one you are doing. Here is the answer with the subquery. I'm sorry, here's the answer with the left outer join. So we are grabbing all the rows from the state table and we are left joining those with the vendors table. Remember, a left outer join gives us everything on the left side of the join statement, which would be state in this case. State S, left outer join vendors. The left side of that expression is the state table. That says give me all the records in the state table and only the intersecting rows in the vendors table, left outer join. But I want to filter that and I only want rows where there is no corresponding vendor for that state. So that's my left outer join, and then filtering on rows that do not intersect. I strongly encourage you to go back and watch the video where I went into the joins, left outer, right outer, and inner in greater detail, because that clarifies a lot of information, and you saw that quite a few weeks ago. If you watch it again, it may be even more clear to you after all the queries that you've written to this point. That then is the solution using a left outer join. Here's the solution using a subquery. And I spoke too soon earlier, this is not a correlated subquery, this is just a regular subquery. There's no correlation here. So we're asking for all the rows from the state table, and then we're saying filter those rows such that only give me the rows that don't exist in the vendor table. And I think I spoke out of turn again. I do apologize. That is a correlated subquery because there is a reference to the state code in that query. I apologize. That is a correlated subquery. And that gives the same results as the previous slide, but using a different style of query. Which is better? I'd have to say that I don't know, because I don't know how SQL Server optimizes queries to that extent. I have to look at the query optimization algorithm and study that to see if one might run faster than the other. If I had to guess, my guess is that that runs faster where I use the left outer join. But that is a guess, and I would not go into production with a guess. I would not release my code to the project on a guess. I would spend time studying the query optimization schemes for both of those queries and try to figure out if one was better than the other. That is beyond the scope of this class, but it's an interesting discussion that while we have two ways of solving the problem, at this point in our learning, we really don't know if one is better than the other. I just expect you to be able to do both, because you will see both, you will be asked to do both over the course of your career, and you will be asked to maintain code written by other people who may use one or the other. That brings us to the end of this video. I encourage you to work some exercises, look at the queries I've written, try to rewrite them yourselves without looking at the solutions, and make sure you understand the difference between a correlated subquery and a regular old subquery. Make sure you understand that things can be solved different ways using a subquery or not using a subquery. Be aware that we don't, at this point, know which would be more optimal, and we don't care. It's not part of this course. But it is an interesting academic discussion, and as a database developer, it will become important to you at some point which one is more efficient to use.